Merci. So we are starting the second part, which is on new methodologies, and there is Pascal Roy first.
I would like to thank the organizer for their invitation, because now there is availability of data, computing facilities, storage capacities. Big data can be included in epidemiological studies in the fields of environment and health. Big data can be summarized by the 3V, triple V for volume, variety, and velocity. And of course, it's important to add complexity if we think at spatial study design, like a hierarchical model for spatial data or multiple scale modeling. When we think at big data, what is new? Maybe some of the data are yet available before planning the studies. Adapted computing facilities and optimized algorithms became available, but what is not new? We can't imagine to have promising results if the data are of poor quality. Of course, it's important to have an adapted study design according to the question asked. Even if the study is a very large study, we work on samples, and the question of statistical inference is raised. And of course, a study is aimed to estimate a population parameter unknown, and that means that at the end of the study, we will have estimation of parameters with corresponding confidence intervals. What is big in big data? The number of subjects included of the studies, the number of covariates analyzed, maybe both. In this presentation, I will focus on the situation of very large number of covariates, higher than the number of subjects included in the study, far higher than the number of subjects. This is what we name a biomarker identification, linked to personalized medicine, and maybe it corresponds also to the study of interaction between genes and environment. A biomarker is a biological product with different distributions between groups associated with the disease risk or disease outcome. With high throughput technologies, it's now possible to analyze DNA at DNA level in GWAS studies up to 2 million of SNP, sequencing whole genome 3 billion of DNA bases. In a transcriptome analysis, the level of expression of around 20,000 genes, and in proteomic studies, few hundreds of peptides, because of the technology. The definition of biomarker raises two questions. The first one is identification. The second one is estimation of the effect size. In fact, these two concepts are strongly linked. If we looked at, for example, the distribution of the student probability under the null hypothesis, the numerator of the distribution is an estimator of the difference in means. That means that we cannot look at significance without thinking at estimation. And if we specify the level of type 1 error rate, we can define the threshold of significance. We know that when we analyze only one variable, one covariate, the power of the test depends, of course, on the choice of the first type error rate, but also on the association, how strong is the association between the covariate and the disease, for example. And when we increase the size of the study, we increase the power. But having at the end of the study significant results is only information that what we obtain cannot be obtained by chance alone, and what is important is to estimate the effect size. That means to estimate the parameters, which can be, in such case, the difference between the means. Using high throughput technologies, we have results on several hundreds, several thousands, millions or billions of results, and with the aim to identify biomarkers. Of course, there is the curse of dimensionality. That means that it's not possible to analyze such kind of data. So there is an idea to work in a subspace, and subspace can be obtained selecting variables. So this is feature selections, or working in the subspace of components. So a regression model on the subspace of components. It is possible to have both methods at the same time. For example, in sparse regression model, there is a combination of these two approaches. When we think about identifying a biomarker, in fact, this is a result with high throughput technologies of a very large number of statistical tests. And if there are M1 biomarkers, that means the biological products of interest, and M0 biological variables without interest, the result of the test is to reject or not to reject the null hypothesis. That means that for the biomarkers, if we reject, here we have true positive and here false negative. And for the variables without interest, here we have false positive results and here true negative results. Benjamini and Hochberg proposed to extend the idea of type 1 error rates to a large number of statistical tests. And they defined the FDR, the false discovery rate, which is the mathematical expectation of the proportion of the false positive among the rejected tests. And this is more interesting than the FWER, for example, in transcriptomic studies. In the same way, Lee extended the notion of power, defining the power as the expected proportion of biomarkers which were detected by the study. With high throughput technologies, we have the same results as analyzing only one covariate. Increasing the level of type 1 error rates increases the power, but it's not interesting. If the association between the variable and the outcome is stronger, the power increases. Increases the sample size, increases the power. And this is a very interesting result. If the number of biomarkers and the control of the FDR are fixed, increasing the number of tests performed, in fact, decreases the power, decreases the ability to find the good covariables. The results I presented were for covariate selection, but we obtained similar results if we think at regression models or at several kinds of classifiers. Stefan Michels and et al., they reanalyzed 7 studies which were designed to establish prognostic signatures for cancer patients. They used an internal validation procedure with resampling, and they analyzed the predictive properties of signatures on observations that did not contribute to establish them. So they obtained these results, that the list of genes, it was a transcriptomic studies, identified as predictors of prognosis were highly unstable. Their chosen studies were over-optimistic, and here we observe results about estimation. That means that they obtain level of associations which were lower than what was published. The sample size, in fact, the size of the study to establish the predictor was very important. And also in 5 out of 7 studies, results were not better than what could be obtained by chance alone. To understand what is optimism, I will present a simulation study performed by a researcher in our laboratory, Caroline Tranzer. She simulated samples from n patients and m omic variables. M was higher than n with a prognostic model. And she simulated 200 identification sets of n patients. And each time, after obtaining covariates, she re-estimated the strength of association on validation sets. So there was a control of the FDR, and after a simulation, samples were analyzed using a Cox regression model. If we look first at the distribution of the estimates of the identification sets of the M1 biomarkers, which means covariates of interest, and of the S biomarkers which were detected. This is a subsample of M1. We observed these results. So these are the distribution of the estimates around the true value, 0.2, for the M1 biomarkers. And the higher is the sample size, the narrower are the distribution of the parameters. But if we look at the distribution of the estimators, of the estimates for the biomarkers which were retained after the analysis, here we have an optimistic bias. That means that there is an overestimation of the strength of association, and the smaller is the sample, the higher is this overestimation. And this is a regression to the mean phenomena. That means that is because we select the biomarkers that we overestimate the level of association between the biomarker and the outcome. If we look now at the variables without interest, M0, and the subsample of those which correspond to a rejected hypothesis, these are false positive. So these are the estimates of the parameter around 0 for the M0 covariates. And these are the estimates parameters for the false positive. And when we increase the size of the sample, the first distribution began narrow, and of course, the false positives correspond to estimates less extreme than what they were. So this optimistic bias, 5 minutes? Thank you. This optimistic bias is linked to the variable selection. And
including questions. Sorry, I'm getting confused. So, so it's 15 minutes, so 5 minutes, but including questions.
Ah, okay. May I read the conclusion? Yeah. So, optimism exists in high throughput studies. Penalized methods have been developed, so lasso and other methods like stability selection or other candidates' penalized methods. These recent methods are promising, but it's necessary to analyze their properties. And then the idea is to use penalized methods for variable selection and also for parameter estimation. And in many studies, we have a joint analysis of classical variables. We do not need to be penalized, and also omic variables, which are subject to optimistic bias and have to be penalized. So it can be interesting to develop such kind of models with several levels of penalization according to the type of the variable included. Thank you.